In this video, we're going to introduce the Hodge star operator. So that's actually introduced in section 5.6, more geometrically and with pictures. We're going to just sort of quickly discuss its algebraic definition, because what's really important is how we actually compute it for differential forms on R3. So here we go. So the first thing is you define the Hodge star using an inner product. So a reminder from linear algebra is that an inner product on a vector space takes two vectors and outputs a real number if the vector space is a vector space over the field of real numbers, or a smooth function, which is what we're going to be considering if the vector space is a vector space over the field of smooth functions. But don't really worry about the actual technical algebraic details. We're just taking two vectors, and at each tangent space, at each point, we're outputting a number, and then over the whole manifold, we're going to be outputting a function. And the way that we're going to do that, well, okay, so first of all, an inner product has to follow these three rules. It has to be symmetric. It has to be positive and positive definite. So the inner product of a vector with itself is zero only if the vector is actually the zero vector. And it has to be bilinear. So if I have a linear combination, I can just pull the linear combination out of the inner product, and this will work in either entry using the symmetric property, the first property. Okay, so how does this relate to differential forms? So there's an inner product on the space of differential forms on Rn, which is determined by the following. So if I have a K form that's written as a wedge product of two K forms that are written as a wedge product of K1 forms, then I can compute their inner product as the determinant of the matrix whose ijth entry is alpha I sharp dotted with beta j sharp. So I basically take the vector that corresponds to the covector alpha I and the vector that corresponds to the covector beta j and take their dot product, and then extend bilinearly. So every element, every K form on Rn, element of the space here, can be written as some linear combination of wedges of K1 forms. So this is where alpha I and beta j are one forms. And so using this third property and this first property of an inner product, I can extend this inner product to all K forms, all pairs of K forms. For K equals 0, the inner product of two functions is just going to be their product. So multiplying them. The most important examples on R3, so we'll just do some examples and then sort of extend it. You'll sort of see the pattern. So the most important examples so we've already done the case of 0 forms, so let's do 1 forms. So let's take the inner product of dx with itself. This is just the determinant of the 1-by-1 matrix. That's 1, 0, 0 dotted with 1, 0, 0, which is just 1. And similarly, if I take the inner product of dx with, dy with itself or dz with itself, I'll also get 1. Now let's take the inner product of dx with dy. So this is the determinant of 1, 0, 0 dotted with 0, 1, 0, which is just 0. And similarly, the inner product of dx and dz and the inner product of dy and dz are both 0. Okay, so let's now continue on to 2 forms. So 2 forms, I can either have, my 2 forms be identical, So basically this case is sort of standing in for the case of dy wedge dz wedge inner product with itself, or dx wedge dz inner product with itself. So here what I'm going to get is the determinant of the 2 by 2 matrix, where the first entry is dx sharp dot dx sharp. The second entry, or the sort of top right entry, will be dx sharp dot dy sharp. And then the bottom left entry will be dy sharp dot dx sharp, and the bottom right will be dy sharp dot dy sharp. So if you go through all of this, what you end up getting is the determinant of the matrix 1, 0, 0, 1, which we know is just 1. Okay, the other case, so and then a similar argument will tell you that dx wedge dz inner product with itself and dy wedge dz inner product with itself are both 1 as well. And then similarly, okay, so let's do one where we have two different two forms. Then I'm going to get the determinant of dx sharp, dx sharp, dx sharp, dz sharp, dy sharp, dx sharp, dy sharp, dz sharp. And this is just going to be 0 because I'm taking the determinant of the matrix 1, 0, 0, 1. 1, 0, 0, 0. So the final thing to consider is 3 forms on R3. So here I'm taking dx wedge dy, wedge dz, and inner product, taking the inner product with itself because there only is one. All 3 forms are multiples of this one. So this is the determinant of the 3 by 3 matrix, which is just the identity, the 3 by 3 identity matrix, which is just 1. So how are we going to use this to define the Hodge star, which is what we started out trying to define? The Hodge star is the map star from k-forms. Let me write that in a more clear way. K-forms on Rn to n minus k-forms on Rn. And it's determined by the following property. So it's determined by the property that alpha wedge Hodge star of beta is equal to the inner product of alpha with beta times dx1 wedge all the way out to dxn for all alpha and beta, which are k-forms on Rn. So I'm going to put this in a box. This is important. It might not be clear that the Hodge star actually is like this property actually determines a map. But we'll do some examples and hopefully that will convince you that it does. So we'll do the example of functions. So 0 forms on R3. Okay, so the Hodge star of a function has to satisfy g wedge Hodge star of f is equal to g inner product with f dx wedge dy wedge dz for all functions g. So let's plug in g just is the constant function, it's just 1. So then the left-hand side is g wedge the Hodge star of f, wedge product is just multiplication. So I'm just for 0 forms. So I'm just multiplying Hodge star of f by 1. So I just get Hodge star of f. And the right-hand side, well, inner product of 2 functions is again just multiplication. So I just get f dx wedge dy wedge dz. So what this tells me is that the Hodge star of f is just multiplying f by dx wedge dy wedge dz. And we'll use this later. Let's do another example. So let's do a 1 form on R3. We won't do all of them because as you'll see, the computation, I mean, it's not that hard, but it will take a few minutes. So let's do the 1 form, just dx. So if I have another one form, alpha equals a1 dx plus a2 dy plus a3 dz, then I know from my equation that alpha wedge Hodge star of dx is equal to the inner product of alpha with dx, dx wedge dy wedge dz. Okay, so let's compute both sides. So let's compute this side. So first, I need, before I get ahead of myself actually, let's write Hodge star of dx as b1 dx plus, sorry, this has to be dx wedge dy plus b2 dx wedge dz plus b3 dy wedge dz. Okay, so now the left-hand side is equal to, a1 will only match up to b3. Then a2 will only match up to b2, but I have to have a minus sign. And then a3 will only work, will only have a non-zero wedge product with b1, so a3 b1 times dx wedge dy wedge dz. Now the right-hand side is equal to the inner product of alpha with dx, and as you might expect from our computation up here, the inner product of alpha wedge dx is just going to give me the first entry in alpha, so the A1 entry, but let's actually compute it. So this is going to be the determinant of alpha sharp dot dx sharp dx wedge dy wedge dz, and alpha sharp is, so this is just a number, so I can just dispense with the determinant. So this is going to be A1, A2, A3 dot 1, 0, 0, dx wedge dy wedge dz. And so this is just going to be A1 dx wedge dy wedge dz. Okay, so what this boxed equation up here tells me is that A1 dx wedge dy wedge dz is equal to this thing. Oh, I didn't need this extra parentheses. So, and furthermore, so I'm trying to solve for B1, B2, and B3. And I have perfect freedom to choose A1, A2, and A3 as I see fit. So let's set A1 equal to 1, and A2 equal to 1, and A3 also equal to 1. So then what I end up getting is B3 minus, actually, let's do it one at a time. So we'll do three different situations. So we'll try three different alpha. Alpha equals dx, dy, and then dz. So for alpha equaling to dx, this means that a1 is equal to 1, a2 and a3 are 0. So what I end up getting is b3 is equal to 1. Because I'm just really interested in these coefficients, right? Because this elementary three-form part is just the same. If alpha is equal to dy, then what I end up seeing is that a2 is 1 and the rest are 0. So I get negative b2 is equal to 0 because there's no a2 over here. A1 is just 0. And if alpha is equal, so this is the same thing as saying b2 is equal to 0. And if alpha is equal to dz, similarly, I get, from this part, I get b1 is equal to 0. So what this all tells me is that Hodge star of dx just has b3 equal to 1, and b1 and b2 are both 0. So Hodge star of dx is dy wedge dz. And similarly, you can show that the Hodge star of dy is negative dx wedge dz, and the Hodge star of dz is dx wedge dy. So the one final thing about the Hodge star is a property that you'll show on your homework, or you'll show partially on your homework. So the Hodge star, basically a Hodge star squared, is equal to minus 1 k times n minus k times the identity. So i.e. Hodge star beta is equal to minus 1 k n minus k beta. So it's sometimes its own inverse and sometimes it's the negative of its own inverse.